So here is the transmittance data, and we can consider the thin film as a Fabry-Perot cavity. It has periodic transmittance spectrum, and the free spectral range is the distance between the two different peaks. And from the lecture notes, we can find a formula for the free spectral range, and we can calculate the product of refractive index and length from these values. And this gives us, as a center wavelength, we use this wavelength in between. The optical thickness of the film is 1026 nanometers. And then let's estimate the refractive index. We can look at the value here, since this is a minimum value and it's also a quarter wave thickness. This is also quarter wave thickness, or some multiple of the quarter wave thickness, as well as this one. But since the transmittance is 78%, the reflection will be about 22%. And based on this information, we can take a look at the figure 3.2 from the book. And here we can see the reflectance for the quarter wave thick layers. And they have the maximum reflectance of a film. And here are the optical half wave thickness, which is the transmittance maximum. And the reflectance, what we saw from the transmittance, 22%, it translates to the refractive index of the film of around 2. So from the modulation of the interference, we can simultaneously estimate the refractive index of the film on top of the substrate. Since the refractive index is around 2, then the length is approximately 513 nanometers. And let's use this as our starting point. Next, we'll take a look at the MATLAB implementation of the optimization. We have the code, and first we load the thin film transmittance data, set the indices of the incident side and the substrate. Then we select the initial values for optimization, and as we previously saw, the refractive index is 2 and guess for the thickness is 513 nanometers. Then we use the F-min search algorithm that's seeking the minimum of some function. We have used a function. We use the T-matrix film stack to calculate the reflectance and transmittance of the film. Then as an option, we can use the incoherent model for the substrate. This is not used for the first exercise. We shall plot the optimization as it's progressing, and then we form the error function, which is just the sum of the residuals squared. We also can use a certain weight function, which is weighting different portions of the spectrum. We can, for example, put more weight on the long wavelength side than the ultraviolet side. And finally, we plot the result. So let's run this. And here we have the optimization results of a single film fit with a constant refractive index. The fitted index is 2.05 and the thickness is 470 nanometers. We can see that the fit is sufficiently good at longer wavelength side, but evidently the peak positions are shifting towards the ultraviolet, and therefore we know that the refractive index should also increase at that wavelength range. So let's proceed to the next model that takes this phenomenon into account. In the second part, we use the same data. In this case, the model of the refractive index follows the Sellmeier model, which has the constant and sum of reciprocals with some weighting functions p and resonances lambda I. And this model is now used in MATLAB, and as an initial values we have the resonance wavelength, and that needs to be outside the measured range, so we select about 200 nanometer resonance. Then the constant b we select as 2 and take the thickness from the previous fit of 470 nanometers. And in this case we use also fmin search and another function which Sellmeier model. The function itself is similar, except that the refractive index is now calculated with an appropriate model. And after the optimization is done, we calculate the resulting refractive index, the reflectance and transmittance, and plot the results. So let's run this code. Okay, this is the result of the Sellmeier optimization. We see that the peak positions of the interference fringes follow better the measured values. However, we see that the transmittance modulation is not correct, and the absorption of the thin film is not taken into account. So we need to take into account the incoherent substrate model as well as the loss in the thin film. And this we take into account by using the Taugh-Lorentz model. So in the final model, we have the Taugh-Lorentz model, which is the very complicated analytical model for the permittivity. It was given as a script, so it is very easy to use. And the model itself uses various parameters, and let's take the values for amorphous silicon as a starting point. And these values were given in the Taugh-Lorentz model script. And as starting values, they are put in the initial values, and then we insert also the initial guess for the thickness. And in the function, we now make a couple of modifications. So first of all, we need to calculate the refractive index with the Tau-Lorentz model, and then we need to take into account the incoherent reflectance of the substrate. And this is taken into account by using the lecture notes. The transmittance can be corrected by using the simulated transmittance and reflectance of the backside of the substrate, which in this case is just the glass-air interface. Note that as a transmittance through the thin film, we need to take the calculated transmittance value, because that is the one which is taking account the loss through the thin film correctly. In principle, for lossless materials, this first term could also be 1 minus reflectance, but in this case it doesn't work. So we have the substrate air interface at the backside and the transmittance calculated from the T matrix in the front side, and hence the total transmittance corrected by the incoherent substrate is calculated as from the lecture notes. And finally, we calculate the refractive index based on the fit and plot the transmittance and refractive index. So let's run the final optimization. Unfortunately, we see that the fit is not very good, and let's tweak the initial values a bit. Change the initial thickness to a different value. Now we see that the fit is almost perfect, so both the modulation of the transmittance and loss is taken into account really well, and the fit thickness is 501 nanometers. Also, the refractive index is increasing towards UV, and the imaginary part shows the characteristic loss towards that wavelength range. I hope this convinces you that the optimization is a great tool for finding and explaining the measurements, but it's also a little bit tricky in terms of selecting the initial values to get the good convergence of the optimization.